attach the link to the announcement on the class, and then you can do whatever you want with that. So we're gonna start not with Jetstream, but we're gonna try this binder thing again. And so this is the link that I posted as a comment on the announcement. And the thing you're supposed to do next is click on this launch binder button. So I'll do that. And what this is gonna do is it does what we've been doing in class with the Jetstream instances, but it does it automatically behind the scenes without requiring any logins on Google Cloud. Has everybody gotten, okay. And you should end up at a place like this, which is now a web interface running on a random cloud instance. And those of you that were in the workshop I did in December, the little day class that I did in December, will have seen this before. But we're gonna ignore everything here. We're gonna go to new. Okay, the recording is out of focus. Let me see if I can ask somebody. Maybe I shouldn't move that much. Maybe that's what I should do. Okay, so go up to new and do terminal. And now you should end up with just a black screen that has a dollar sign on it. Everybody good? Okay. So device the recording, which is not working at all. I don't really understand what's going on with that. That'll be better. Okay, so what we're going to do is if you go back to that GitHub repository, you don't have to go back there. But if you do, if you want to know what we're going to work through these links: introduction, the file system, and working with files. And this is really intended to be open Q&A as we work through things for you all to ask whatever questions you have about what's going on. I'm happy to sidetrack as much as necessary. You'll see it actually ends at a fairly similar point to some of the stuff we've done in class, but we're not assuming any of the stuff that we've done in class particularly. And all of these materials and stuff should stay working sort of indefinitely, so they're not going to go away tomorrow. Okay, so we're going to start with introducing the shell. So maybe before we even start with introducing the shell, how many people feel like they have this is always a hard question to ask. How many people would like me to go over roughly how computers work in the like 2-minute version of how computers work? You would appreciate it? Yeah, excellent. Okay. So what I'm going to do then is I'm going to open a blank. How do I get a blank screen? I can probably turn off the projector. I can probably blank the projector somehow. Can't I? Mute, freeze. Select. Okay, I'm fine. I go to a blank website. Good enough. Okay. And again, just ask questions. You can actually do the whole thing like this so that we don't have to screen up and down if we're going to whiteboard. So, at a sort of high level, computers consist of a processor. They consist of they have what's called working, memory, and they have hard disk space. Is that you guys can see that? Okay. You've probably heard the processor referred to as CPU, central processing unit. Working memory is usually referred to as RAM. Aaron, could you? And then hard disk you're all familiar with. and then there's usually network, but we're just going to lump network in with hard disk for reasons that I'll explain. Okay. And the way that this sort of interacts is that the processor, and this is a very generic phrase, but the processor does stuff. The processor looks at data, adds numbers, computes alignments. Whatever you're doing with the computer is what the processor does. So when you load a web page and you need to render the web page, the processor does a lot of layout and other stuff. And I'm sort of explicitly excluding, you know, the screen or video output from this. But anything that's displayed on the video and so on sort of has to come through the processor more or less. There's some exceptions for like GPUs and gaming rigs where you have other hardware that does stuff. Okay, so anytime you do anything with a computer, the processor does stuff, but it has to have data of some sort to work with. So what to display, what to compute, what to align, what to search. And that always comes from the working memory. And the working memory is fast storage, but it's limited. So typically we're talking, so a typical amount, let's just say, is 4 to 64 gigabytes of RAM of memory on a laptop or on a server that you're using. Hard disks are where the working memory gets data. Actually, I'm going to use another word. I can't come up with a better word right off the top of my head, but volatile means goes away with power. So if you turn things off, all the stuff in your working memory goes away. It's like sleeping or whatever. Whereas the hard disk, of course, is permanent. And it's also a lot larger. So, and it's relatively slow. It's a lot larger. You know, we're talking 100 to 1,000 gigabytes, and it's persistent. Okay. So the sort of hierarchy of things, and when I say slow, I mean like 1,000,000 times slower than this, which is in turn, you know, 1,000,000 times slower than what goes, or 1,000 times slower than what goes on in the CPU. So if the CPU has a little bit of working memory, just so it can like hold two numbers and do things with two numbers, and that's super ultra fast. And then working memory or RAM is a lot slower, but it's still a lot faster than the hard drive. And the hard drive is where you just dump everything, because that's where it's going to stay when the power goes off. And so when you're downloading data sets and stuff, what you're usually doing is downloading to the hard disk, so that you can then later on work with them by loading them into working memory, and then work with them from the processor. And there's a lot more to be said about this. Like there's literally like whole courses of study on how all this stuff works together. The reason I'm bringing it up is because what we're going to talk about today is probably one of the two lowest levels at which it's reasonable to tell the processor what to do. And that's the Unix shell. And there's sort of this weird duality where let's say that the black is data, but you also have to tell the computer what to do with that data. Or you have to have instructions, you have to have procedures, you have to have programs or software that tell the CPU, yes, to align two pieces of sequence, here's how to align the sequence. Here's what an A means, here's what a G means, here's how to translate the sequence of protein, all of that stuff. And that's software. But to a computer, software is just another type of data until it reaches the processor, at which point it has the special status of sort of executing. And executing just means now instead of treating it like data, I'm going to treat it as a recipe for doing something. And this is the separation between the similarity between data and software is not actually something that's necessarily built into computers. It just has been by practice for 70 years. there used to be computers in the early days where the software and the data was actually stored separately. And you can see why this might be a security problem as well. If you can load data onto a computer and then get a computer to execute it as software, then maybe you can get the computer to do things that the owner of the computer doesn't want. And that's actually the source of a lot of that's the source of a lot of security problems. Anyway, all that aside. So the software and the data is stored on the hard disk. The software and the data is transferred to the working memory. The software is then sort of executed as a recipe to do something with the data. And then what happens to the data after you're done with it? Well, basically what happens is you either send the results back to working memory or back to the hard disk. So if you're doing things like what we were doing in class with mapping sequences to a reference genome, you have a recipe for mapping stuff to the reference genome. Those results get stored in working memory and then eventually saved to the hard disk so that when you turn off the computer and come back later, they're still there. And also because they're big, right? So there's a size component where you can work with a lot. If you can load the data in sort of progressively from the hard disk, you can work with it in smaller chunks that fit within working memory. And then the CPU can do small things, can do things to small bits of data very fast and then put them back in the working memory. And so what we're going to be talking about today is, they said, one of the two ways of really orchestrating this process. What the shell does is the shell basically is responsible for telling the computer to load the software recipe in and execute it. And sometimes it's responsible for also passing in data, which is to say, but that's dependent on the software it's using. So you'll see a lot of the commands we're running are just like list what's in the current directory. And that's going to say, okay, I'm running software, and the software says, okay, go back and look at the hard drive. It's a recipe for going and looking at the hard drive and listing what's in a particular location on the hard drive. And so we're not really accessing data, a lot of data directly. We're really using the software component. And then other software is like, let's edit this data. And that says, okay, we're going to load the data into working memory, and we're going to work with it, and we're going to save it back to the hard disk. And so you have both the blue, the black, and the purple lines going on at the same time. And the shell, as I said now a couple times, is one of the two ways of doing this. The other is using a programming language. And that's something like Python or R or C or Java or JavaScript or other languages you might have heard of that interact more directly, with the working memory and the processor. And that's something that we'll talk about maybe next week a little bit more. But for now, we're really just talking about programs that somebody else has written in some language, and you don't need to worry about which one. And we're going to run them via this shell interaction.
What about the SSD?
So the SSD, you can tell I'm old. The SSD is a hard disk. It's still a lot slower than working memory. Yeah, SSD is generally a lot slower. It's still like, thousands of, I don't know the exact numbers, but it's still like 1,000 times faster than a hard drive or 100 times faster than a hard drive. But it's still, 100 or 1,000 times slower than working memory. And that's simply because the SSD has different requirements, right? When you turn off the power, it needs to stay there. And it needs to be a lot bigger and cheaper.
Why do you recommend to install the OS? Does that mean?
It makes everything faster because the SSD is faster than the hard drive. But a lot of computers now don't even come with a hard disk. They come with SSD storage. So my laptop, for example, has only SSD. So I'll put that down. Okay. So coming back to the shell, we're going to talk about today is the sort of fairly low-level way of interacting with the computer. By low level, what I mean is it doesn't give you a nice graphical interface. It doesn't give you a nice, displays of stuff. It's all very text-oriented. And I'll explain why it's very text-oriented as we go along. There's both good reasons and bad reasons. The good reasons are because it can be very powerful, and the bad reasons are that it's been working for 70 years, so we're not going to change it now. It's basically that there's sort of this legacy component where once you know how to work with a shell, it's going to take, if you decide to seriously do bioinformatics or other kinds of work, it's going to take weeks to months to get comfortable with the shell. And once you've gotten comfortable, by gum, you're not gonna move to some other software system because you have to learn that now too. So there's sort of this historical contingency, like we all know the shell, so that's what we're going to use. Okay, so the way the way today's going to go is I'm going to walk through these tutorials. And let me see if I can get a separate screen so you can just see, split the screen so you can see what, I can read the instructions without. Okay, I think that'll work. I need to come over here, grab this, bring it somewhere. Then I can have the terminal over. Oops. Don't look at my desktop. Nobody wants to see my desktop. Okay. So everybody should be at this $sign prompt, and you should be able to hit return and have it just go down the screen. Sorry, so there's a link in the announcements, Canvas announcements, and in one of the responses that brings you this. Did you come in when you saw the link? Click on binder. Okay, Karen, can you? If they, okay. So the first command we're going to learn is something called clear, and I'm going to use clear a lot. And the reason I'm going to use clear a lot is because it resets the prompt up to the top and clears everything on the screen. You don't need to do that because you don't have the same constraints that I have in terms of showing people what you're doing. Go ahead.
Sorry, mine isn't responding to like anything.
Yeah, so try, you might have to relaunch. If it sits for a long time, you might have to relaunch Finder. Probably won't happen if I don't go off on 20-minute monologues again. Okay. Okay. So now I find myself in the awkward situation of having stuff that I actually want to show you. So let's do this. Okay. Let's do the other way. Okay. So what is a shell and why should I care? So this is what's called a command line interface. There is an interface where you can enter commands in a line-oriented way. I enter a command by typing a line of stuff. So if you go to the link and you click on Launch Binder, and then you go up to New on the upper right-hand side, and then Terminal. You should get to this. You should get to this black screen with the $sign. Okay. And so it's line-oriented because you typically enter one command per line, and there's no mouse interaction with it generally. And so there's this question like, why would you want to learn this? And the answer is that there's a lot of stuff that you can only do with the shell. One answer is that there's a lot of stuff you can only do with the shell, so a lot of bioinformatics tools can really only be used at the command line. Another is that if you need to automate stuff, so if you have like 100 files or 10 files to work with, then with the shell, it's actually very easy to work with 2 files or 100 files or 1,000 files. So I've done things like do 100 different blast searches against 100 different query proteins, set that up in 1 minute, and then walk away and leave it to run for 3 hours. And that's something that's very hard to do when you're dragging and dropping stuff or using the web interface. In theory, once you get used, or in practice, once you get used to it, the shell makes your work less error prone, and there's a couple of reasons for this. One is because you're not doing the same boring thing 10 times. You're writing one exciting thing once, and then it's doing 10 things for you. And we'll show you that if we get that far. The other is that by writing things down explicitly and being able to keep a journal, because it's line oriented. Yeah, actually, if you could do that, that'd be great. Because it's line oriented, you can save the commands you're running in like a Word document or in an email message to yourself. You can keep a log notebook of what you ran, and then you can actually just rerun those things by copying and pasting the command line. If you had a GUI, if you had a graphical interface for a web page, you'd have to like, okay, I moved over here, I clicked this button, I set this parameter, I did this, and you have to remember how to do all of that and interpret your instructions. Whereas here you can keep a logbook and literally copy and paste from the logbook to rerun things, and you'll see what I mean by that. And then the reason that we insist on teaching this is because if you're going to be doing practical, pragmatic bioinformatics, you're going to be working with large amounts of data, larger than what fits on your laptop. And so realistically, that often can't be run on your own machine. You have to go somewhere else to do it. And almost always, lowest common denominator is you can get a shell access to some remote machine. So you can get a Jetstream machine or an Exceed account or an Amazon computer or something on the farm or Genome Center cluster, and you can always get to this shell prompt It all works more or less the same way. That's why we do it. That's why we teach it. There's this great plot about geeks and repetitive tasks where there's these two axes, the size of the task and the time spent. And you'll see that for small tasks over here, geeks and non-geeks take about the same amount of time to do it because everybody does it manually. At some point, people like me get annoyed by doing a task that takes like 5 minutes at the command line. And so what we do is we then automate that task. And from that point on, we run script. We run the task using the sort of logbook approach. And this takes some extra time. So it's technically sort of a waste of time. If I'm only doing a task like once or twice in my life, then realistically, I don't need to like automate it. But at some point, once you have to do the task enough times, or it's a big enough task, if you don't have to sit there and babysit the computer, and if you can repeat what you did last time, you start to win out. And exactly where this crossing line, this divergence happens, and where this crossing line happens is task dependent and expertise dependent. But essentially, almost everybody I know that does data analysis for a living uses either R or the shell, or a combination of both, or Python to do the data analysis. And so what we're going to talk about today is one of the sort of one half of what you do, which is work at the command line to automate these things. So we've talked about how to access the shell a couple different ways. In class, we've been doing Jetstream, where you get something that looks kind of like this. Here, we're actually doing a different thing where we're going through Jupyter Notebook. It's all the same. If you have a Mac, you actually have access to this locally. You just don't have the data on it. If you don't have a Mac and you need to log into Jetstream, you can do that, start up your own. For now, you can use this Jupyter Notebook situation. You can use it at any point to experiment. If you just want to see, like, if you want to try some stuff, here's a safe environment to do it. This environment will be thrown away once we stop looking at it. And you can create a new empty environment whenever you want, just by clicking on that launch binder button. So it's anything you type with this $sign is safe and will not be persistent.
What terminal do you recommend?
So on Windows isn't 100% shell compatible, and it's not Unix underneath. So Mac and Linux are Unix underneath, so you can run the shell and it works essentially the way we're going to describe you. There's a couple shells for Windows. There's something called the Bash shell for Windows, and that works fine. That would be my first recommendation. If you drop me an email, I can point you at exactly what we recommend for some of the software carpentry and data carpentry lessons where we teach this. But at the end of the day, you always end up at a prompt that looks like a $sign or a %sign or a greater than or something else. And at that prompt, when you hit enter a few times, and not entering any commands, it should just repeat the prompt. That's sort of how you know what the prompt is. Just sort of silly. Oops. Okay. So as I said, there's a command, and it's called clear. And if you type clear and hit enter, and if you mistype it, like I have a bandage on my finger, which is totally the reason why I'm mistyping things today, it'll say, I don't understand that command, unless you happen to hit on some obscure command that is your mistyped command, which sometimes happens. There's actually a command. It's very common to mistype a command. I don't have it on here. It's very common to mistype a command called ls. And if you type it as SL, you can install a package that makes a train go across your window, just because, and like it takes like 3 seconds, and that's supposed to remind you not to mistype commands, but mostly it's just humorous and then gets annoying very quickly. Okay, so when I talked about the hard drive or the hard disk earlier, or the file system, the disk, really what we're talking about is a file system. The file system is where these permanent files sit. And a lot of what the shell is about is finding and manipulating files that are stored permanently on your computer. Basically, the two things you do is organize files and then tell the computer to do things, sometimes horrible things, to those files. Remove them, rename them, align them, search them, assemble them, whatever it may be. So we're at this prompt, and what we're going to do is figure out what directory we're in. And directory is the current folder on the hard disk that we're in. And if you're familiar with the Mac or the Windows file system, that's when you like have a folder up and there's a bunch of files in it. We're doing the equivalent, but we're doing it at the command line. So we're going to run this command pwd, which stands for print working directory. If you type pwd, you should see this, home/home/Jovian. And this is just the username. It's a play on Jupyter Notebook. Never mind, don't worry about it. This is the username that you should all have. This is because we're on this remote computer that we've set up. All it knows about us is that we're some anonymous random person on the internet, and it's calling us Jovian. So what this is telling us is that we're in the directory, the folder Jovian, under the folder home, which is at the root of the file system, at the base of the file system. And if you look at your Windows computer or your Mac, if you go to the root directory there, which is not the desktop, it's actually the root directory of the file system, you'll see that under that there's a bunch of stuff. And essentially everything on your computer can be reached by going to the root folder, the slash on Unix. Let me move this back over. Okay. So if we do an ls, you'll see a couple files. What ls is doing is it's saying list files. And you might ask, why not list _ files as a command, or list, or something? And the answer, the not great answer, is that back in the 60s, when these commands were first developed, well, there's two answers. One is sort of apocryphal, which is that back in the 60s, when this stuff was being developed, you were doing everything via teletype machines that were really slow. It's actually hard. It's going to be super hard to explain this to people that were born in the 90s. But basically typewriters that were connected to a computer, and so it was slow they didn't have terminals, they didn't have screens, so displaying stuff was slow, and so what you would do, everything was sort of terse. The real answer is that, as you'll see in the next hour or two, Unix is in love with sort of terse cryptic commands. And it's just like any other, whatever discipline you guys, you all work in, they have their own lingo. Well, so does pseudo-computer people and Unix. And so you just sort of gotta memorize. You just gotta memorize it. Luckily, there's only about a dozen commands that you really use regularly. And the rest you can look up. As long as you know they exist, as long as you know what you want to do, you can use Google to find them on Stack Overflow, Stack Exchange. So what ls is telling us is that there are 3 entries in this directory. And the 3 entries are apps.txt, which is actually a configuration thing that you can ignore. There's a readme.md, which is actually what we saw on the GitHub repository. These are the files that are actually in the GitHub repository on that web page that we went to. And then there's DC sample data, which is what we're going to be working with today. And we'll actually, you can take a look at readme.md later if you want. The other command that you end up using a lot, so 2 commands you end up using a lot are pwd and ls, and a third command is cd. If you type cd dc_sample_data, what you're doing now is changing your working directory, and the working directory here refers to the location, the default location that you're going to look, that commands are going to look for files. So it's sort of like the current folder, and each shell will have potentially a different current folder. So if you started up another terminal in another tab, it would have a different working directory. It would be on the same file system. You would be looking at the same store of files, but you'd be using different working environments to do so. And now you can type ls again, and now you see other information. And this information is now 2 other directories, 2 other folders. So DC sample data was a folder. Now we moved into that folder, and there are 2 folders underneath it: SRA metadata and untrimmed fastq. So you might be thinking, okay, this is super bare bones. How did Titus know that what app.txt and readme.md were, and that the DC sample data was a folder that I could change directory into, and what would happen if we tried to cd into these? If we tried to cd into these, it would tell us they're not directories, they're not folders, you can't change into them. How did I know that this was a directory, other than that I set this environment up, and how would you know? Well, so there's an option that you can give to ls called -F. And what these options do is they tell ls to modify its behavior. They say, yeah, list files like you normally would, but do so with some extra sauce. Do so with some extra salt. And in this case, what minus capital F says doesn't need to stand for anything. Don't think it has to make sense. Just remember it as it says, annotate the output with what they are. So in this case, it puts a slash after things that are directories. You don't need to follow along with this, but you can if you do cd ... you ls minus capital F. What I did was I went out of the DC sample data directory up one level in the folder, and I can see now that ls minus F didn't annotate apps.txt or readme.md with anything, which actually means that all they are is files. All they are is text files or just data files. Whereas you can see that DC sample data is a subdirectory. And here I can type cd apps.txt, and you'll see it says not a directory. So you'll get a lot of unfriendly messages from Unix. Why did you try to do that? You're just being silly. Important not to take it personally. It's just mean.
To clarify, period is
So
moving up a directory?
yeah, so we'll talk about it. We'll talk about it a little bit later, but exactly. So ... means the directory above where I currently am. So we'll go into CD sample data again. So make sure that when you DC sample, make sure that when you type PWD, that PWD looks like this. And if your PWD looks like this, can you just put a blue sticky up on the back of your screen? I can see it. Anywhere where I can see it. Awesome. Okay, cool. Okay, so take down the blue stickies now. Everybody have them. Great. Okay, so I just introduced you to this cryptic minus capital F thing, and you're like, how'd you know that? Well, I know because I'm reading a tutorial, and I occasionally use it, but I don't actually use it enough to remember it. But if I used it, if I wanted to know what it was, if I wanted to know what the options were that I could supply to ls, there's a command called man. And what man does is print out a manual page. So if you type man ls, you'll get the manual page for the ls command. And what it tells you is that ls lists directory contents, that it takes a set of options, and then maybe a set of files, and these are optional. The square brackets means you don't have to provide them. And then it gives you sort of a terse description, list information about the files, the current directory by default. So when you type ls, what it's doing is it's just looking in the current working directory. Sort entries alphabetically if you don't say otherwise. And then there's all sorts of can I just go away? Is everybody else's still working?
Yeah.
Yeah, mine just happened to go away. Again. So this is a good training environment, but it's not a good, this is an okay training environment, I guess I should say, but it's not a good like long-term work environment because it can just go away. Okay. So this is the man page for ls. And then it'll say some other stuff like mandatory, don't worry about this. And okay, now here's the disaster. So I'm hitting spacebar to scroll down. Here's the disaster. You can hit space and you can see all of the options for ls. And there's a lot of options. I think there's only one option, there's only one letter between A and Z that is not a valid parameter, a valid option to ls. You might be thinking, do I know? Like, I'm not going to remember all of those things. So in practice, I remember like 3 options for ls. The main one that I use is ls minus L. And what ls minus L does is it tells me things about what's in it gives me sort of details in terms of the size of things and when they were last modified. The main way that everybody I know finds out options for ls is they use Google. They say, how do I list the size of files with ls? And you can say, how do I make ls show file sizes in megabytes? And you click on this, and there's the question is, what commands do I need to show the file size in MB? And then there's all sorts of options. And generally, the top answer is the sort of best. So I'm going to just copy and paste ls minus l dash black size, whatever. And if I paste this, you can see it's now giving me the file size rounded up to the nearest megabyte. So literally like 95% of the time, if I want to do something tricky with a command that I haven't done a bunch of times memorized, I just go to Google and I'm like, how do I do this? And the trick there is getting the wording right. So, and that takes a little bit of experience, but it's fairly straightforward. Why is my screen so? How do I? Sorry, I'm trying to figure out how to get my. Yeah, that didn't work. Okay. Well, my screen's super narrow for reasons that I don't entirely understand. Okay. There we are. That's better. Whoops. Okay. So that's sort of, I think. No, I don't do that. I know. Okay. All right, I'm losing track of all of my different windows here. And I managed, okay. So that's what a man page is. Okay. So there's a little challenge question that I just want to ask you. So if you use this ls minus l command, can anybody tell me one piece of information? This is sort of a silly question, but what are the, okay, this is a silly challenge question. Never mind. So I'll walk through what ls minus l is telling us is that these are both directories. They're read, write, and execute by our user. If they're read and execute by group and read and execute by other users, this is a single user machine, so these don't matter right now, but if you were on the HPC and if you were on like the farm cluster or the genome center cluster and you wanted to give other people in your group access to things, you need to make sure that they had read access to files and execute access to directories. Otherwise, they wouldn't be able to see them from their account. Right now, we're logged in as these files belong to user Jovian and group Jovian, which is us. They're approximately 4 KB in size, 4,000 bytes in size. They were created February 14th at 5:25 in the time zone that this thing's running in. And I don't know what time zone it's running in, but this is when it was created. So this morning at 5:25 UTC, which I believe is Greenwich. And then these are the file names. So ls doesn't give you any of this information. ls minus f tells you their directories. ls gives you the bare bone listing. And then ls minus l displays more information about these things. And you're going to be interested in different things at different times. When you start working with big files, ls minus l is how you're going to figure out how big the file is. She'll help you estimate how long it's going to take to do searches, that kind of thing. And that's a matter of experience rather than a matter like I can't tell you that up front for all the possible tasks. Any questions at this point? Okay. So you'll notice that anybody, I'm going to do clear again. You'll notice that anybody that spends a lot of time at the shell prompt does things very fast. Like I type ls. Okay. Typing 2 characters is not so bad. But if I want to find out what's in the SRA metadata directory, I can type S. And there's no possible way I typed SRA metadata that fast. What did I do? So I used what's called a shortcut. I used the tab shortcut. If you type ls, S, and then hit tab, it will autocomplete. And the way it will autocomplete is it will say, well, you typed an S. What in the directory starts with an S? And there's only one thing. And so it'll automatically fill that out. The same thing is true of if you type U and hit tab, you'll get untrimmed fastq. So one strategy that you can use when you're working with lots of files and so on is to name the files in such a way that you can do things like autocomplete. We'll use autocomplete throughout. But if you wonder, as we're typing long things, the goal is not to be able to type really accurately. The goal is to be able to use tab complete so that the computer does things correctly. The computer will never incorrectly tab complete. It will never like misspell what a tab completes. So it's a way to do things reliably. Okay, so let's go. And the other thing is it doesn't just work with ls. It works with any command. So cd, if you want to change into the untrimmed fastq directory, you would type cd space u and then hit tab. So I ran this ls, I gave it the directory names, and now it told me the files that are in these. Let's go into the untrimmed fastq directory. So to do that, how do we change into the untrimmed fastq directory? cd, so type cd, u, hit tab. Now if you type pwd, you should see that you're in DC sample data and you're in the untrimmed fastq directory. And now, if you type ls, you'll see there are two files here, srr 097977.fastq and 098026.fastq. What do you think happens if we do autocomplete here? Tab complete here. So I'm going to type ls, tab, and the computer goes, okay, well, all of the files in this directory start with srr09. So completing that far is fine. There's no ambiguity there. You didn't even need to type s. What happens if I hit tab again? But it had to stop because now it doesn't know, do I want a 7 or do I want an 8? If I hit tab again and hit it twice, it will tell me what the possible autocompletes are. This doesn't really matter in a directory where we have 2 files. But if you have a directory with 50 files, this can start to matter a lot more because you can sort of work your way. You can, like, okay, well, one of these files, let me get down to srr09. Okay, now I can type either a 7 or an 8. Let's type 8. And if I hit tab, now it autocompletes based on that. Okay. So the other thing you can do at the beginning of the command line, I'm going to type clear again to get rid of all of this. The other thing you can do is if you don't remember what command to run, you don't remember the exact spelling of the command, but you remember it starts with a P, you can type P and then hit tab, and it will tell you how many commands start with P. So it turns out there's 100 commands that start with P. So I'm not going to ask for that. But I can type PW, and if I hit tab, it's going to tell me, well, there's actually only 5 commands that start with PW. And in this case, the one I want is PWD. That's what I'm looking for. So it's not super useful for short commands, but once we start getting into things like trim-o-matic or other commands where they're sort of longer commands, this can be quite useful. So as everything that I said and did is linked in the shell genomics. Just to go, so you can come back and revisit it, but just to go through. In practice, once you get used to it, the shell gives you the ability to work more efficiently by using keyboard commands rather than a GUI. ls, pwd, and cd are things that you're going to get used to if you use the shell a lot. Most commands like ls and take options or flags, which begin with dash, and then you can do tab completion to navigate around more fluidly. Any questions or comments at this point? Okay. So I'll warn you. I'm trying to go slowly. One of the things that happens a lot when we're talking about computational stuff is at some point things drop off a cliff at an individual point for everybody in the group. So what I mean by that is I'll say something and half the room will nod and the other half will instantly be lost. So please alert me when you're lost because I can't always tell. You can put up a red sticky note if you want to call my attention, like you're having a problem or you have a question, or you can just wave at me and I'll flag that you want a question. I'll finish my current monologue. So moving on to the second thing, navigating files and directories. And this is the reason we do this so early rather than doing useful things. And we're doing useful things in the course and for the lab. So hopefully you'll see some of the applications of this, but this turns out to be the major point of confusion for people working in the shell is that you sort of have to figure out where files are in relationship to each other in order to work with them. So that's what we're gonna spend a little bit of time going through. So what we're going to do is we're going to navigate the directory structure. We're going to perform operations on files and directories that aren't our current working directory. There's these hidden directories and hidden files because it can't be as simple as you can see everything. It's actually like, and there's a reason for this. It's sort of to reduce complexity, but we have to teach it because it adds to complexity if you don't know about it. And then we're going to talk about absolute and relative paths. Absolute paths are paths that work the same no matter what working directory you're in, whereas relative paths are relative to the working directory you're in. And we'll explain that. And then we'll talk about some navigational shortcuts that you can use to move around the file system. And just to tie this back to what we're learning in the lab section of 201B, you've seen a couple of these commands at work in terms of creating a work directory and putting data here and putting data there and running this command and installing this command. And a lot of what we're doing there is we're downloading files, we're putting them in a particular location, and then we're moving to a new location because we want to work with them. It's generally a bad idea to have one working directory where you do all your work. It's like when you have a lab bench saying, I'm only going to work in this one 1 foot by 1 foot square bit for all of my different experiments, rather than having your gel box area and your pipetting area and your whatever else you do area, your frog dissection area. And so you can think of directories as ways to keep what you're working on in an uncluttered area that's related to each other. Okay. So turns out to be super hard to move things around over my shoulder. Okay, so let's go to the DC sample data untrimmed FASTQ directory. So here, type CD. What CD by itself does is it goes to your home directory. You can always tell what directory in by typing pwd. Then type CD DC and hit tab to go into DC sample data. And then we're going to go into untrimmed FASTQ. I'm going to type U and hit tab and enter. So suppose that I said, okay, you know what, I'm done, I'm doing some stuff in here, and then I'm done with untrimmed FASTQ. What I really want to do is go back to DC sample directory. What's one way to go back? So, okay, let's, first of all, we're underneath DC sample data. We're in a directory that is underneath this other directory folder. So suppose that I want to go back to this, and I hadn't told you about ... What other approaches could you use? I'll give you a hint. There's one of the approaches is on the screen.
You could type out //
Right. So you could say, okay, looking at my current working directory, where I actually want to be is this. What I'm going to do is I'm going to type what's called the absolute path is /home/jovian/DC sample data. That's long-winded and slow and annoying. Right? But I can do it. I can type cd/home Jovian, and I'm going to use tab completion. And now I'm where I should be. And so the difference, we're going to talk about this in a little bit, but if you put a slash at the beginning, that automatically means you're referring to what's called an absolute path. It's like the full GPS coordinates for a particular folder. It's unambiguous on a particular computer. What's another way of getting to this DC sample directory? So what did we do up here? We typed CD, which brought us to our home directory. And then we typed CD DC sample data, which brought us to the directory under our home directory called DC sample data. And if we just stop ourselves from typing this last command, CD untrimmed FASTQ, we will be in the DC sample. So we can type, so suppose we want to do this another way, we type CD, and then we type CD, we type pwd, you can see where we are, and then we type CD DC sample directory. Now if we type pwd, we're at the place that we expect we want it to get to. Right? So the part of the point I want to make here is there's actually usually many different ways to get to where you want to go, and they're all right. Whatever works is right. The thing you should just make sure of is that you actually are where you want to be. And in this case, we're in the DC sample data directory under our user account Jovian. But what I'm going to do is now reintroduce this dot dot. Suppose that I was in untrimmed fastq, and I said, you know what? I want to be in DC sample data, not in untrimmed fastq. I could type cd dot dot. And what dot dot says is back one. You can see the effect of this, pwd. So what happens, what do you think happens if I type cd dot dot now? It goes to home Jovian.
Do you have to do that one at a time, or could you just do like dot 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 dot? And go
So,
down
right,
and
so
down?
very good question. If you do cd dot 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 dot, it's going to tell you no such file or directory. And the reason for that is sort of obscure, but basically, there's actually a single dot as well. And so because there's a single dot, it doesn't know if you're asking it to do 2 dots or 4 single dots or 2 dots and 2 single dots or 1 single dot and 2, right? There's ambiguity. So you need to separate with a slash. So if I did cd dot dot slash dot dot, that would actually bring me from DC sample data to Jovian to home. See if that's right. You can also do all sorts of crazy things, like you can say, I'm in untrimmed fastq and I want to go to the SRA metadata, which is at the same level under cd dot dot slash SRA metadata. And tab completion will actually help you do all of this. That gets confusing because people are like, I have to remember where I am, and then I have to like back out and then go back down. So we recommend, at least when you're getting started, we recommend just doing this in single steps. You can always interleave the single steps with PWD and LS. Okay, so let's go back to DC sample data. So PWD, CD gets me back to home Jovian. And now I can do cd DC sample data and do PWD, and now I'm in the sample data directory. And now I can type ls, and I have, or ls minus f, and you can see that we are in this directory DC sample data that has SRA metadata and untrimmed fastq. I'm going to do something that's not in the lesson per se, but if you go back to that GitHub page, I wanted to show you something kind of neat. So this looks an awful lot like the directory that when we type ls in the home directory that we get, and that's not by accident. What Binder is doing is actually packaging this whole thing up. There's a couple extra files, and you'll note there's a file that starts with a dot that's called hidden, and there's another file that starts with a dot called bashrc, and those are hidden files that ls doesn't normally show you. But then you can also see DC sample data has a little folder symbol. You can click on DC sample data, and somewhere is my mouse. If I click on DC sample data, you'll see it's now SRA metadata and untrimmed fastq. And if I click on untrimmed fastq, you'll see this. And these are actually the files that are copied into the binder. So what I'm showing you is, right, this is sort of what a web or a graphical interface to the folders would look like. What ls and cd are doing is doing these clicks for us and moving around, moving where we are. So it's all the same underlying. The only difference right now, and this is maybe why this is potentially a bad example, is if we change things here, this is a copy that we'd have to start a new binder in order to get them. This is not linked intrinsically. What we all have is independent copies of this. So if I made a change here, it wouldn't reflect on your copy. If you made a change on your copy, it wouldn't reflect here unless we updated between the two. Okay, I'm going to type clear again. We're in DC sample data. If I do ls dot dot slash dot dot, you'll see what I'm doing is I'm doing an ls in the home directory, and we're picking up on Jovian is the only thing that's in home. And if there are other users on this machine, you would potentially be seeing those. Okay. So we're going to do a trademark Unixy thing, which is it's a little more complicated because of these hidden files. So I'm just going to tell you, if I go back to my home directory, Jovian, whoops, CD. And I take PWD, I'm in Jovian, and I type ls minus A. Minus A actually shows you all of the hidden files. There's actually a bunch of hidden files here. There's .hidden, and there's .bashrc, which were in the GitHub page that I showed you. There's .bash logout, .git, and .local, and .nano, and .profile, all of which were created in the process of spinning this up. So they're sort of created dynamically. And the reason that these things are there, the reason that hidden files exist is because this is where programs store like preferences and configurations. So by default, they don't want you to see them when you do an ls, because most of the time you don't need to work with them. It's something you work with sporadically. Whereas what you want to see when you do an ls is, oh, here's my data, here's the stuff that I'm actually working with. So ls minus A is a way of adding this information about that. But now I do actually want to see the hidden files. I also should say, we didn't cover this before, but if you do ls minus AF, it combines the effects of minus A, which is show everything, and the effects of minus F, capital F, which says show directories and so on. So you can see dot and dot dot are actual directories that are sitting there. And that's why when you do cd dot dot, this is just magic that says go up one level. Dot is actually the current directory. And you might be, why do we need a reference to the current directory? And it comes in handy. You can see DC sample data is a directory. Hidden is a directory. Git is a directory. Local is a directory. .nano is a directory. And .profile is not. So you can always combine these. So suppose that I was in a directory and I wanted to remember or find out what my sample file names were. One way to do that is I could say, oh, I'm over here and I want to go into my DC sample data and I want to go into my untrimmed FASTQ and I want to do an ls. This is kind of clumsy. It's like if I'm working on something, I suddenly need to like abandon what I'm working on and like move over here and rummage around and figure out what's there. Whereas I could just say, just look over there and tell me what's over there. So the way you do that is with ls, and you've already seen this, but if you do ls DC sample data untrimmed FASTQ, what you're doing now is you're telling ls, hey, wherever I currently am, go relative to that, go look at DC sample data folder and then the untrimmed FASTQ folder underneath that. This would be equivalent to doing ls/home/jovian/DC sample data/untrimmed FASTQ. And that's because my current working directory is home Jovian. So because I didn't put a slash at the beginning here, it's a relative path that's going from where I'm currently sitting, going to DC sample data and untrimmed FASTQ. Whereas this ls command will work no matter where on the what my current working directory is, because it's an absolute. So it's this again, full GPS coordinates, relative GPS coordinates, or relative, move 100 meters that way.
Clarify. So when you just use the command ls, that's just to look what's there, but you're not in the directory.
That's right. If you type ls without anything, it looks in your current directory. If you give it the location, it tells you what's in that location. And for those of you that are interested, if you go back through like lab 1 or lab 2, you'll see us using these commands. You can always throw in an ls to see like what's in the directory. Right, and so the cd command works in a similar way. I can do cd DC sample data and untrimmed FASTQ, and that now moves me in one step. It moves me into this directory and then into this directory. Before we had done cd DC sample data and then cd untrimmed FASTQ, and it done it in 2 steps. You can do it in 1 step. And so, okay, so what I would like you to do is the following. Navigate to your home directory, and from there, list the contents of the untrimmed FASTQ directory. And just go ahead and do that, and put a blue sticky up when you're done. blue sticky? Everybody set, including the non-blue sticky? Okay.
No, I'm
Okay.
very distracted right now, sorry, I've been getting messages from my.
Okay, no worries. Understand. Tell them to go away. Tell them you're learning stuff. We should solve all their problems themselves. No, don't do that, because I think we know where that leads. So, okay, so the solution is CD, which brings you to your home directory by default, and then ls dc sample data / untrimmed FASTQ. Just to reiterate. Right now, I'm in this directory. I type CD, and that moves me to my home directory. If I don't give CD any arguments, it resets my working directory, my home directory. And now I can do ls dc sample data untrimmed FASTQ. And that will tell me those files. So we've actually already talked about this a couple times. So far, sorry, I'm trying to, there we are, okay. Nope. This concept of full versus relative paths. And essentially, the only distinction is the way you tell something is a full path or an absolute path is because it has a slash at the beginning, and a relative path doesn't have a slash at the beginning. It either has a dot slash whatever, or just starts off with a directory. So this is now a relative. Okay, so if we now do CD, we're in this directory, and you do CD DC sample data dot hidden, this brings us, why is that not in? Huh. Yeah, it was in this directory. Okay, so that's a bad, maybe I set it up wrong. Right, it's in this directory, the dot hidden. I need to reconfigure things. Okay, so I'll just reiterate, if you do CD DC sample data and untrimmed FASTQ, that's the same as doing /home Jovian DC sample data untrimmed FASTQ. Both bring you to the same location, but this is an absolute path that no matter where you are currently will bring you there, whereas this will depend on where you are. So if I now type this command in again, it's not going to work. I type the CD DC sample data / untrimmed FASTQ, it's going to say there's no such file or directory because there is no directory in the directory that I'm in. Sorry, in the directory that I'm in, which is this directory, there is no subdirectory called DC sample data. I could make one. There's no reason you can't have a directory named the same thing as a subdirectory, named the same thing as a subdirectory, although it does get confusing if you do that intentionally. But right now, since there isn't one, you can't change into it. Okay, so let's do another quick check here. So using the file system diagram below, suppose that pwd, your current working directory, displays users thing. What will ls .. backup display? Here are your 4 options. So look at this diagram. We have users, thing, backup, and backup. 2 different directories named the same thing, one underneath thing, one underneath users. And then in backup, we have original PNAS final over here. And in this backup, we have 2012, 2013, and different dates in there. So suppose that you're in the users thing folder. What does ls .. backup display? Any votes? So
Hard to read with the lyrics.
sorry, yeah. Do you want me to put the screen back down, or?
Oh, no, it's fine, it's just like.
Yeah,
moving around.
because you're literally like in the worst possible place for the Claire. Do you have a vote for number 2, which is to say this? Any other votes? Number 4, which is this. Any other votes? Okay. So the first thing is there's plenty of backup directories called backup flying around. So what you're saying is if you're sitting in thing, odds are pretty good you're either going to do an ls of this backup or this backup, which would give you either this or this. Why not number 3?
You don't have the.
Minus capital
Yeah.
F. You haven't given the option to say, hey, tell me that these things are directories, these things are directories or not. Okay, so what does the ... mean here? Go back one directory. In this display, what go back one directory means is go up one directory. That was probably not necessarily clear from the diagram. So users is the directory above thing. So what ls ... does is say ls ... /backup. And so the answer is going to be this one because you're going up one and then into the backup directory and asking to list the contents of the backup directory. Okay. Go ahead, yeah.
If you didn't do ... but did a single dot, it would be number 2.
If you either did a single dot or no slash at all, if you did ls backup without the ... then it would be this. It would say, look at thing, I'm in thing, look at the directory backup. No. So it's actually not an unhelpful exercise to do sometimes to actually diagram out your directory structure once or twice. So typically, the way a lot of people work until they've been doing this for a while is they have one layer of directories, which is directories right beneath their home directory. And that's where they do all their work. They either have project 1, project 2, project 3, or lab 1, lab 2, lab 3. Once you have done this for like 30 years, like me, you start to have too many files to have them all in one. It's like you have a single file system and you have 1,000 files and 1,000 folders in it. So I organize my things hierarchically. So I have a documents and I have a development directory. I have a couple other directories. Okay. So there are some shortcuts that you might see. And I am going to show them to you, and I'm going to tell you to know that they're there and then ignore them until you see somebody else using them. And the first shortcut is the tilde character. Now, if you all have US English keyboards, it should be on the upper left. It's the squiggle. And that's shortcut for home directory. If I type cd tilde, that brings me to the same place as cd. Just cd. Why would I need that? Why would I not just want to be able to do cd and get to the same place? Why would I want the tilde? Any thoughts? Because you can combine it, and because it's not just cd that you're working with, it's potentially other commits. So suppose that I am in my DC sample data untrimmed fast queue, and I want to do an ls of my home directory. How would I do that? How do I get a listing of my home directory? So I'll give you one for free. You can do cd. I can do ls of ... which says I'm in here. I'm in this directory. Go back one, and now I'm in my home directory. I could also do ls/home/jovian, because now I'm providing an absolute path. What else could I do? So those are sort of the two defaults, but go ahead. Right. So I can also do ls of tilde, and that will show me my home directory. And I can actually specify now ls tilde/DC sample data. and that will tell me what's in this DC sample data. That's now an absolute path. My home directory is specified completely, and then a subdirectory under there. Go ahead.
Is there any way that you can change what directory is designated as your?
You can, but by default, but it's a bad idea because a lot of things actually depend on it. So when you start a new program, it will often read as configuration from your home directory. So unless you actually have a different home directory, that there's some weird configuration problem and you're fixing it, changing what your home directory is a bad idea for that. So something you can do, we might not get to it today, you can alias or link other directories into your home directory. So suppose that you had like another disk where all your data was, and you're like, but I really don't want to have to like refer to this disk with like /disk/this/that. I want it to be in my home directory. You can make a virtual entry in your home directory that points to that disk, so that you can refer to things with tilde. It's like making an alias. I think it's an alias in Mac, on Mac and Windows, where like you can have a folder that you make a link to a folder in some other place, so you can access it more easily. So in practice, this is just to get a little philosophical here. This is a fine example of what Unix heads do a lot, which is because it's so easy to refer to your home directory becomes with just a single with this tilde command. Your home directory becomes a natural organizational point for files, which is good because it gives you a safe default. Like all I have to remember is that I put this data in a directory called project 5 in my home directory. I don't need to remember what my home directory is, what disk it's on, what my username is. Suppose that you have some long, annoying username. You don't have to remember any of that. You can just type tilde and it goes to your home directory. Okay. Yep. So that's tilde, and that's it. Okay. So that's sort of that's our discussion navigating, and we're going to get to some renaming and moving files around next. But should we take a 5-minute bio break? Do people need to break or anything? No, everybody's happy. Okay. So that was what I was just showing you was this the file navigating files and directories. We're going to move on to the third one, which is working with files and directories. So we're going to cover here is how can I view and search file contents? How can I create, copy, and delete files and directories? How can I control who has permission to modify a file? This isn't going to be super important in the environment we're in here because we all have our own independent environments, and nobody else has access to them. But again, if you're on like a farm cluster, the Genome Center cluster, and you want to share things with other people in your lab, this might become important. And then how can I repeat recently used commands? So suppose you have a command that you're trying to get to work, and you run it, and then it breaks, and you're like, oh, I just need to fix one thing on it. How can you go back and edit it rather than having to retype it all from scratch? Okay. So because this is a genomics lesson, we're going to be working with these FASTQ files, which is convenient. And that's what is in these untrimmed, this is what's in this untrimmed FASTQ directory. So get to the DC sample data untrimmed FASTQ directory. So I'm going to do that. I'm already there, but one way you can do it is you can type cd:/DC sample data /untrimmed FASTQ, and I'm using tab completion. Do that. Make sure you're there. 1 second. This is like the longest lingering cold I've had in a while. Getting all congested. I think I have drugs. Yes, I have drugs. Okay. So in this directory, we have 2 FASTQ files. And suppose that this directory was more complicated. We could list all of the files in this directory that ended with .fastq by using what's called a wildcard. What a wildcard says is, when I type ls, I can give it a list of files that I want to ls. And in this case, I'm saying, give me all the files that have anything at the beginning and end with .fastq. In this case, it's the same thing as what's in the directory. If you have a bunch of intermediate files or other things that you've been doing in this directory, you might actually have have a bunch of other things. You can also use the wildcard in other creative ways. So you can say, you know what, I want to know what in there ends with 77.fastq. And now you'll restrict yourself to only the .fastq file that ends with 77.fastq. The point here is that there's no assumptions that the star is making. If you say star q, it'll list everything that ends with a q. If you say srr star, it will list everything that starts with srr. And a cute trick, if you want to know how it's interpreted, and this is going to be a little bit confusing, but it's a fine example of how, well, confusing stuff is. If I type echo star.fastq, this is a service. You can see how the star is interpreted. And the thing here that is maybe a little bit hard to explain, but is that the star is interpreted by the shell itself. So ls is not going, oh, there's a star, let me match to all of those things. Echo is not saying, oh, there's a star, let me match to all those things. It's literally before echo or ls even see this, it's been expanded to match all of them. So when you write your own scripts, when you write your own programs to do things that you're running from the command line, you can take advantage of the wildcard stuff because it's built into the shell. It's not some special property of the programs that you're running. And so that's quite nice. So you can do right. Okay. So let's try doing this. So from your current directory, do each of the following tasks using a single ls command for each. And you can just do the first one, just to see make sure it works. I'll just give you a minute. So how would I list all of the files in user bin that start with the letter C? Wildcards. Okay, first you have to type user bin properly on the C star. You see there's a lot of stuff in user bin that starts with C. If I want to limit that and I want to say I want stuff that starts with CA, right? So wildcards are sort of arbitrarily powerful. Any guesses as to what calendar does? Apparently it's a listing of events. I've never seen that command before. Cal does something kind of cool, which is it tells you what the current day is and highlights it, tells you the days of the month. Anyway, happy Valentine's Day, by the way. So should have brought chocolate or something. Well, next Valentine's Day, next time I run a workshop on Valentine's Day. Okay. So, right, so the solution to all of these is user bin C star will list all the files that start with the letter C. User bin A star will list all of the commands that start, all of the programs or all of the files that start with the letter A. And then ls user bin star O will give you things that end with the letter O. There's actually other wildcards you can do. So for example, there was this bonus, which is list all of the files that contain the letter A or the letter C. And here, you can actually, there's other tricks where you can say, square brackets say either or, so that you can sort of make fairly complicated. And I'm going to just take advantage of something. Hang on one second. What's my hypothesis? One minute logged in. Sorry. Should be okay. Sorry, just making a note that there's a typo here. Okay.
For the bonus problem, it's A or C. How would you say and C?
So if you want A and C, it would be you just you would eliminate the square brackets. You say AC. Right?
And so would that give you only ones that had AC together?
Yes.
What about AC like any?
So that is harder. The best way of doing that I can think of off the top of my head is ls user bin star a star user bin. Really, I can't type today. Bin C star, like that. I don't know how to do. What would you do?
See ones that only have C or only.
Right. So you want. So here, you could do something like this. But at some point, you'd have to list it. You'd say, I want an A followed by a C or a C followed by an A anywhere. I think that should work. That looks vaguely correct. I can't find anything that doesn't have an A and a C in it. Yeah. And so what's interesting about this is a lot of what programming and computer use is twisting your mind to figure out how to get the sort of set of options that you have using wildcards and the commands available to do what you want done. So so this is sort of not necessarily an obvious solution. It's a brute force solution. There might be a better solution. I can't think of one off the top of my head. And this works. So it's sort of like the pragmatic, like, well, this works. This gets me do what I want, and it's just I just twisted my mind to think this way. And so you can think of it as this is maybe a bad analogy. I'm trying it out for the first time. You're in a workshop. There's a set of tools laid out on the table, and you're like, I need to build a wagon. Like, this is a set of tools I have to work with. Okay, I'll try to build a wagon, and sometimes you'll succeed, and sometimes you'll need to say, I need to go find a new tool. And really the problem is that there may be many, many tools lying on the workbench, but you only know how to use like half of them. Okay. So at this point, I'm going to intuit that some of you are underwhelmed. It's like, okay, I already know about files, I already know about folders, I know about computers. This seems like an awful lot of like, we just spent like an hour and a half going over how to like get a listing of a directory, change my working folder. I know how to do all of that. So now we're going to start looking at some other things. One of the things that we're going to start with is history. So if you type history, you'll see, voila, the history of all the commands you've run. You might be thinking, why would I need this? Well, what you will find as you do bioinformatics work is that you'll run a bunch of stuff and you'll get some results and you'll be like, wait, what did I actually run? What set of parameters, what set of files did I run this on? And there's two things you can do. One is the dangerous thing that you're going to be tempted to do. Well, there's three things you can do. One is ignore the question. You can be like, I got results. I don't really care how I got them. That's really bad because at some point you're going to change something, regenerate the results, and you might be not running the same thing. You might be like, well, I need to align a different set of reads, or I need to align with a different parameter or whatever. But I want everything else to be the same. Sorry, the recording is, there's some autofocus thing that doesn't work that well. Another thing that you can do is you can say, okay, well, now that I got to this result, I'm going to go back and I'm trying to figure out from scratch how I got to this result. Okay, I really care about getting this exact result, so now I'm going to go back and I'm going to do it properly. I'm going to record the commands. Now that I got a result, I'm going to go back and record the commands that I did. And the problem there is now that's just a waste of time. Like, you got the result somehow. And conveniently, the computer does a fine job of remembering the commands you ran. And what history can do is give you that list of things that you ran. So at this point, you could say, you know what? I am done with the diff for the day. I really don't want to have to remember all this stuff. What I'm going to do is I'm going to get this history, and I'm just going to copy it and paste it into a Word document, and close my computer and go home. And then tomorrow, I'll be able to look back at this history and figure out what I did. And there's ways to save it. So this gets into the tricky bit of files, and I'll show you the command and say history to say history.txt. And now if you go to the home, what directory? Anybody know what directory I was in? Okay, I'm in untrimmed fast queue. If I go to home and I go to untrimmed fast queue, there's now history.txt. And this is now a file that I can save to my computer and come back to later. And that's only if I'm working here. One of the problems with the shell is if you're working in Jetstream, you have to transfer files off in a different way than if you're working in Jupyter. So it's not necessarily, you just know that it's possible, and then I can help you with whatever environment you're actually working in. And without telling you, I introduced you to yet another interface to the file system, which is, there was this Jupyter console. That is how we started the terminal. And the Jupyter console is now the actual living file system that we're on. So you can see we're in the untrimmed fastq directory. In the shell, I created history.txt, and it showed up here. So this is now directly tied to the thing that I'm actually working with.
So is there any way when you save your history file to like save it as a G file and annotate it so you can just run it again?
More or less. I mean, yes. The short answer is yes, but let me tell you, you really don't want to do that. The reason is because, at least if you're like me, about 2/3 of the commands you ran are wrong. What you really want to do is take the commands and then edit them down. Like, think about it this way. When you do your logbook for a lab, there's two things you want to do. One thing is you want to record what you did so that you figure out how you screwed up and you can, or what the details were. But then at some point you want to convert that into a protocol. We can actually potentially hand it to an undergraduate student and say, do this. And that involves like fixing your handwriting, undoing your like scrawls and notations, and making it. And so what you're saying is there any way for me to just go back to exactly what I did and rerun that again? And I'm telling you, that's a bad idea, because presumably next time you do it, you'll do it slightly better. And so what you really want is sort of the thing that is close to a protocol. And this is, history is the starting place for that. So you can record it, this is now my lab notebook. And then you can say, this command didn't do what I wanted. This command did do what I wanted, so I'm going to eliminate this command.
But can you do that and then just run it? Like I'm thinking
Yes.
of like a do file and something.
Yes.
Do that.
Yep.
Okay, and then can you annotate it in the file so that
Yes.
you know what it did?
Yeah. So I think, I don't know if we're going to get to it, but it's actually the next component of the lesson is scripting. And it is, quote, as simple as putting these commands in a file and then typing the command bash space file, and it will do that. The only trick is you have to remove the numbers. So what are the numbers for? Why are there numbers in front of our history? Why do we care that we ran 128 commands? Any ideas?
Easier to reference.
Makes them easier to reference. So I can say, you know what? I want to rerun this command without retyping it, and it's command number 121. So I'm going to type !121. And when I type !121, it automatically replaces that with whatever command number 121 was. This is not like a super frequently used trick. There's other things you can, and the reason for that is there's other things you can do. You can also use up arrow. I can say, let me go back, let me do a clear. I can do up arrow, and I can go back through all of the commands I ran.
Could you combine that with other commands? Like if you wanted to rerun that command but add anything that contains a D as well or something?
Yeah, sort of. It turns out I've done that on occasion. Turns out to be easier to do this, which is hit up arrow till you find the command you want to modify,
No, just
and now modify, and now you can use the arrow keys and delete and space and stuff to add stuff to old commands. Right? So one of the lessons of the shell is you should rarely find yourself doing a lot of of old typing. If you've already typed something and it's long and complicated and you got it right then, go back and recover from when you got it right. And there's a lot of tricks for that. In the lesson, there's command C, there's command R and that will do a reverse search. So if I'm here and I do Control R and I say ls, it will find the last ls command I ran. And if I type Control R again, it will go to the previous one, Control R again, Control R. So you can do sort of free text search through all of your previous commands with Control R. The other two commands that are useful, the other two control keys that are useful, Control C will stop whatever you're doing and reset. So I can be here, and I could say, oh, this command's long and complicated, and I don't want to run it, especially if it's like an RM command. You're like, oh my God, no, I don't want to run that. If you type Control C, it'll reset you back to the empty shell prompt. And then Control L is the same as clear. So I can type clear, or I can type Control L, and it'll bring me back. So history is pretty useful, right? So I showed you this. Let's not do this exercise. So there's been an interesting omission so far, which is that we know how to switch directories. We know how to run programs like ls. We know how to list contents of directories. We haven't actually talked about how to list the contents of files at all. We went through this in class a little bit with head and tail. That's more or less what we're going to go through here. So the simplest way to print out the contents of a program. So now we're not looking at the contents of a directory. We're looking at the contents of files in the directory. And there's a program called cat, which is short for catenate. And if I'm in this directory, DC sample data untrimmed fastq, I can just type cat, and then do srr tab, and I'll do the 8 one. If I do that, what it's going to do is it's going to take all of the contents of this file and display it on the screen. So I enter, and you'll see it displays all of the contents of the file on the screen. Okay. You're like, what possible use is it to have all of this junk on the screen? And the answer is that, well, it's of some use, which I'll tell you in a second. But the other answer is, in Unix, sometimes it's useful to look at a file to figure out what it is. So in this case, I recognize this is a FASTQ file, because this is the format of a FASTQ file. It contains DNA sequences, and it's got a file name that ends in .fastq. Cat is a generic way to look at any file. I have this history.txt file. I can type cat history.txt, and it will tell me it'll give me everything that I saved into history.txt. So it's a generic way to look at files. This is as opposed to a lot of the way that you all might be used to looking at files, which is to use a specialized program. Like if I'm looking at sequence files, I need a specialized sequence viewer. If I'm looking at a programming language, I need a specialized programming language viewer. In Unix, almost everything is just a data file. It's just a collection of text and or binary data. And cat can be used to look at all of the text files. When I ran this command, cat history.txt, why do I not get the cat command in the bottom here? Anybody know why? Why is cat not in my history?
Because we stopped here line 126, so everything afterwards.
Because history.txt contains the history only up to the point where we saved it. And if we ran history again, you would see there are now at command 139, not 126. So this, okay. So So let's do the second one of these exercises. Let's just take a minute, say from your home directory and without changing directories, use a command to print the contents of all of the files in this directory. So it's going to involve cat. It's going to involve this string. And because it's going to be all of the files, it's going to involve a wildcard. So how do you put all that together? So I'll just give you a minute to. What did people come up with?
So for number 2, I went back to the home directory. I did cat DC sample data / untrimmed SQ / SRR star.
Okay, so you did this.
Yes.
Okay, so that is almost correct. And if we hadn't done something else, this would be completely correct.
Well, now that we have the history file, you can just put the asterisks after it.
Right. So this is kind of a trick because we added our own file, history.txt. We actually don't. This will work. This will print the contents of all of the SRR files. But if we put star in there, we'll also catch history.txt. But you won't see it because it comes before the other files. So with the cat, you don't necessarily see it. But yeah, so that's okay. So the problem that we're going to run into, right? So I should just to point out, I think you've seen this, but the solutions are in the document. So okay. So the problem with cat is that it's great, it shows you the things, but like lots of stuff goes off the screen if you run it in practice, right? So when the file's really big, it can be annoying to use. There's a program called less that's useful for this. And what less does is it does what's called pagination. It gives you one screen full of the contents of a file at a time. So to use that, let's navigate to DC sample data untrimmed fastq and do less SRR 097 whatever .fastq. When you run this, you'll see it's giving you a screen full. This is actually the top of the file, giving you a screen full of the text that's in there. And then it's giving you a little prompt at the bottom. And you can use the space bar to page down through the file. So I'm hitting the space bar repeatedly, and it's showing me the different chunks of data in the file, the different pages of data in the file. And so this is a way where you can actually look, cat just sends all the data to your screen, less shows it to you one page at a time. And you might be thinking like, do I have to keep on hitting space to get through all of this? And the answer is, you can keep on hitting space to get to the end. If it's a big enough file that will take a long time, you can type Q at any point to get out of it. So I go into less, page down a couple, and then do Q. And there's actually a bunch of commands. There's forward, space, B is backwards, G goes to the beginning, capital G goes to the end, and Q quits. You can also do searching. So I'm going to show you a totally ghetto way of looking for restriction sites. So if we go to less, and now I say, you know what, I want to know all locations in this file where there are 1, 2, 3, 4, 5, 6 C's. So 1, 2, 3, 4, 5, 6 C's in a row. I want to have those highlighted. It's not so useful when you're looking at sequencing data, but when you're looking at like a genome, you could do this. So I'm going to do //CCC, and it will actually highlight on the screen everything that matches those 6 C's. So why did it highlight more than 6 C's here? Okay. Yes. It's actually, it's not, I don't think it's 12. 1, 2, 6, 7, 8, 9, 10, 11, 12. Okay, it is 12. Well done.
Does it increment?
Because there's many overlapping collections of 6 C's, because I gave it CCC. So you could imagine using this to go into a genome file and search for restriction sites. Why would that be a bad idea? What aspect of biology is going to get in the way? Well, is this true? It's not true for restriction sites per se. Primer sites. Why would you not want to use this for primer binding sites? Reverse complement. You'd have to search for both the forward and the reverse complement primer binding. Plus, there's another problem, which is that you can have slight mismatches in primer binding sites and still have the thing work. So you really want to use a specialized program that takes into account DNA structure and melting temperature and other stuff. Okay. So we didn't talk about it back when we were using man, but when you type man ls and it gives you the whole list of, so I typed Q to get out of less and show you man ls again. So man ls shows you one page at a time, and it actually uses the less command to paginate. So I can now type Q to get out of man ls. I don't have to, or space to scroll down, or lower G to go to the beginning, or capital G to go to the end. So the other point that I want to make here is that there's a surprising amount of internal consistency in all of these commands. There's really the commands that I'm showing you. This is I can never decide if this is like a positive or a negative thing to say, but like the commands that I'm showing you here are the bread and butter commands that I run, that I spend. They're probably 70% of the commands that I run when I'm at the shell prompt, because I'm moving directories, I'm renaming files, and then I'm running commands. But running commands is actually running commands to plot things or do data analysis is actually a minority of like moving around, finding files, looking at the results and other stuff. And we've actually covered all of that here. So it might be interesting if you have the time, and if you go back through like the second mapping lab, to intersperse some of the commands that we executed there. Look at those commands. You should recognize more of them now. And then intersperse some of those commands with lesses or PWDs to see where you are and to look at files. We've actually covered head and tail in class. Head and tail are like cat, but they only look at the first 10 lines or the last 10 lines. So if I'm in this untrimmed FASTQ directory and I do head, SR, whatever, I'll get just the first 10 lines, and I don't have to like do anything tricky, like quit out of less or whatever. And tail will do the same thing. Tail will give me the last 10 lines. And I'll repeat what I said in class, which is that if you're looking at a collection of sequences or at a data file, and you want to know what's in there, head will show you the beginning, tail will show you the end. And you don't really need to look at the middle. Most of the time, because if it's right at the beginning and it's right at the end, then probably it's right in the middle. At least that's been my experience. So head and tail can be good ways of sort of doing a quick check, like, is this a FASTQ file? Now, I don't know when this lesson gets into FASTQ files, but we talked about this in lab a little bit, but a FASTQ file is a sequencing output file, generally output by Illumina sequencers, that specifies a bunch of records, and there are 4 lines per record. So there's the header line, which is the name of the sequence. There's the actual sequence itself. There's a plus line that just recapitulates the header line. And then there's this quality score line, which tells you how the estimated probability that each of these bases in the sequence is wrong. And this is a numerical encoding. It's a Fred, called a Fred score. There's an encoding of it in FastQ. And so this is information that programs like FastQC or Trimmomatic can use to figure out, to display average statements about the average quality score and so on of what's in your sequencing data. Any questions? Okay, so we can move around in the file structure. We can look at files. We can search files, and we can. Did we do redirecting output? We did redirecting output, did we? Nope. Interesting. Okay, let me just make another note. These lessons are always under development, and they're always moving stuff around, so sometimes things get messed up. It's always nice to. Oh, okay. Just happened, sorry. Track of things, redirect output. Not yet discussed. Okay. So we haven't actually talked, so we've now talked about where files live, what's in files, how to see what's in files. But now we want to do things like, suppose we want to do things like move them, copy them, or remove them. So the first thing we're going to say is use copying a lot. And what we mean by this is when you're working with computational data, generally you have a fair copy, a safe copy of the data that you're working with. This is whatever came off the sequencer. And you want to treat that as sacred. You want to make sure that that is not something you modify or edit. The way you sort of want to do computational pipelines for reproducibility reasons is you want to submit the raw sequencing data to an archive, and then in the paper tell people what you did to that raw sequencing data. So what that means, practically speaking, is you want to make a copy of the raw data and keep it safe. Another way of doing that is just to never change the FASTQ files. But probably the first thing to do is make a copy in some place where you're not going to modify. So how do we make a copy? Well, there's another 2-letter command called cp. Okay. So let's go to the DC sample untrimmed FASTQ directory. I'm there already. And type cp, and I'm going to use tab completion. Okay, so this, what do you think this command is going to do? Any ideas? So this is a copy. It says copy a file to itself. Okay, this is a stupid question, but it's going to say no, they're the same file. Okay. The reason I did that though is I can now use the up arrow and left shift my cursor over, so I can now insert this new -copy.fastq. And this will now produce a copy of the file. Now if I do an ls, I now have a copy of the file, and I have the original file. And I could do that for this other file. Go ahead.
If you're gonna want to copy like all of the files in a folder, can you just copy?
So we haven't talked about making directories yet. That's literally the next thing. So suppose I said, you know what, I want to make a backup copy of all of this, and I'm going to do it in a directory called backup, and then I'm going to do copy star to backup. And now if I do an ls of backup, you'll see it contains history, this, the copy, and this. And if I do an ls of this directory, the only difference of the directory that I'm currently in is that the directory I'm currently in has a subdirectory called backup. So if that sounds confusing, that's fair. Let's go back and look at it in the web prompt. If we go here, we go into DC sample data and we go to untrimmed fastq, you'll see there's these files, and now there's a folder called backup. If I go into the backup folder, it will look exactly the same as the set of files. This is in practice, this is kind of a bad, when we wrote this tutorial, we didn't want to confuse people. Typically, you would make a backup copy somewhere else. So a great place to make a backup copy is in your home directory, not under your working directory. And the reason for that is that there are commands that can delete your entire directory and everything under it, which we'll get to. Well, I don't think we're going to teach you those commands, but you'll find them on your own. And it's nice to have the backup copy somewhere where if you accidentally mess up this directory, like, oh, I have a whole backup copy somewhere else. So there's another command that we're going to use. All right, I just lost track of where my cursor is.
So if you want to make the directory in your home, then you could do mkdir like /home/jovian/backup.
Exactly right. So the way you would do that, and I'm going to use the trick of the tilde, is I can make a directory backup like that. And now I can do copy star to tilde backup. Now we keep on getting this error, which I'll come back to in a second. It's not an error, it's just a warning. First, let's make sure we got the right stuff in that directory. So how do we, there's a couple of different ways to figure it out, but what's one way of looking at this directory to make sure that it has trust but verify, right? It's one way of making sure that we actually did copy stuff into that directory. You can see, again, it has a copy of everything. So anybody want to do some Unixology and try and interpret this? There's actually two really important pieces of information in here. One is about something it didn't do, and the other is implying that it could do something. So the something that it didn't do is it didn't copy the backup, the subdirectory in this directory when it made the copy. And that's because CP by default doesn't copy directories. It only copies the file. It only copies files. But what this implies is that if you give it the -r command, it will copy directories as well. So you could do copy, so I'm going to go edit this command. Sorry, I'm going to edit this command. And I'm going to put a -r in. Okay, so first of all, if I look at what's in backup, you'll see there's this. There's no subdirectory in there. Actually do this with -F. When I look at this directory, there is a subdirectory called backup in my current directory. That wasn't copied because when I did the copy, it doesn't by default copy subdirectories. If, however, I say copy -r star backup, what it's going to do is it's going to look in this current directory, and it's going to copy everything in this current directory to this location. And I'm actually going to change this command to make it a little clearer, because we have too many backup directories floating around. What I'm going to do is I'm going to copy everything in my current directory, which is this stuff, to a new directory called save in my home directory. And now I run into a problem that I forgot to make the save directory. So let's make directory save. And then I have to spell that right. And now if I do the copy, it doesn't complain. And if I do an ls -f of save, you'll see this is now an exact copy of what I have in the current directory. So copy -r will copy all of the subdirectories that you specify. Make some sense? Okay. So let's see, how much do we want to do? Okay, let me go through this. So the other thing I want to do, the problem now that we now have is that if I go to my save directory, I have a bunch of files here, but this W, when I do an ls minus L, this W tells me that they're writable. That's a bad situation for those files to be in. If they're writable, that means I can accidentally delete them. So what we're going to do is change their permissions using a command called chmod, which stands for change mode. And the way we're going to do this is we're going to do chmod minus W star. And what that says is anywhere where there's a W in the permissions, anywhere where there's a write in the permissions, remove it. And now if I do an ls, you'll see that you'll see that the W has been removed from all of the locations. You're thinking, okay, well, why do I need to do that? So first of all, let me show you what happens. How would I put a W back?
chmod
Plus W, right? So chmod plus W star. Okay, so that puts the W back. Let me introduce you to a new command, rm. If I do rm history.txt, what that does is it removes the file history.txt. So I can do that because those files are writable. If I do chmod u minus W of star, and now I try to remove srr098.fastq, it's going to ask. It's going to say, are you sure? Because this file is write protected. And while I'll let you remove it if you really want to, I'm going to ask you first. And if you type Y, it will remove it. And if you type N, it will not.
Sorry, so why did you do chmod u minus?
Oh, I'm sorry. Ignore the U. That was I have 30 years of ingrained habits.
Okay.
So what U says is remove only the W that's in the first column here and not the W that's here and there. U stands for user. Never mind. It's the same as minus W. Minus W. But good eye. See, I was checking to see that people were watching. That's what's going on. Okay. So this stuff becomes important. There's actually U, G, and O, and this stuff becomes important when you're on a shared file system. Like there are other people in your lab and you're trying to give them permissions. So you should never give, it's generally a bad idea to give everybody write privileges, but generally you'll find that if you're in a lab, like there are, you're part of a group. Here there's a user named Jovian and a group named Jovian. And if you set the permissions here, so that other people that share your group, suppose your lab had its own group name, then you could make this writable by other people in the group. The general rule with files is don't let other people write to them. The general rule is somebody wants to do something to a file, give them read access and not write access, because then they can make a copy, do whatever they want to the copy, and when they mess up, they can come back and then get a clean copy from your unchanged copy. Okay? So that actually comes up in my lab a lot. You know, we work on some big data files, and sometimes we don't want to have to, we just want to know where like the central copy is. And that central copy is writable by nobody. Not writable by the user that owns it, it's not writable, but it's readable by everybody because we're sharing that. Okay. So I'm going to show you one last dangerous command. Let me go back to DC sample data untrimmed fastq. And you'll note, like, we have a lot of copies of this directory lying around now. We have one here, we have one in our home directory called backup, and then we have a copy called save, right? That's just because I was showing you copy. But let me get rid of this particular copy. So now I run into this problem. I can't remove backup because it's a directory. It's not that I don't have permissions, it's that it's a directory and RM by default doesn't remove directories. So it turns out there's a command called rm-r. And R here stands for recursive, which just says remove this file and anything below it. And if I do rm-r backup, it will uncomplainingly remove this directory and all of the files in it. That sounds dangerous. That's because it is. Use rm-r sparingly, but sometimes you just want to get rid of a directory. There's a perplexed look or two. Are there questions on this? Yeah.
If there are any files within that directory that have the writing permission.
So good question. So what happens with write privileges? So suppose I do make directory backup, copy start at backup, and then I look at backup and I go, you know what, this is a backup. Let me change them to not writable. And now I'm going to remove, whoops. Now I'm going to remove that. It does the right thing. Right, so I went through, I made the directory, it asks. Okay. The super dangerous command that you absolutely should not remember and should not use is force. So you say rm-fr backup. And -f says whether it's with or without r is if I have the permission, if I am allowed to remove it by changing the permissions to remove it, go ahead, do so. And this will get rid of the backup directory without asking any questions. And we'll do so recursively. If you ran this in your home directory, all of your data would go, everything in your account would go away. If by chance you are logged in as an administrator on a computer and you run this command in the root directory of the computer, then you will make the computer unworkable. It's a rite of passage. Everybody does it once in their life. Then they learn not to do it again. So this is actually a really great illustration of the power of the command line and the danger of the command line. It's actually kind of hard. Like most graphical user interfaces won't let you like take your computer and drag it to the trash. But from the Unix command line perspective, it's like, look, you know what you're doing. We're just going to assume you know what you're doing. Go for it. So be dangerous. Now the good news is that in general on most computers, the only person you can mess up with commands like this is yourself, because generally you won't have systems administrator privileges or this might be different on your laptop. If you have like a Mac and you go into a system administrator mode and you run this command, then the whole thing can go away. What else do I want to say? There's actually a nice little adage. Unix is super user-friendly. It's just picky about who its friends are. So, okay. So let's just finish up here. Okay. So let's do this exercise. So can you all just spend a minute going into the untrimmed fastq directory, creating a copy of each of your backup files, making a new backup directory, and putting the things in there. And if you want to know, this is the third lesson on files and stuff, so you can get to it from the GitHub repository link. If you want to remember the commands, if you go back to that, it's the working with files link here. Okay. Let's just take a couple minutes to do that, and I'll put this back up. I'm going to go get some more water. I'll be back in a second. And feel free to like chat. I'm happy to, if people have specific questions, I'm happy to answer them, or I'll just sit up here and wait for people to put up blue stickies. right, shall I move forward? Yeah. Okay. Okay, so so the first thing is make sure that you have deleted your backup file and all the backup directory, oops, and all the files that it contains. I have many keys that do many things on my keyboard. Okay. So how do I make sure that I've deleted my backup directory? Well, if I had the backup directory there, let me just make it. If I had the backup directory there, you'll see it's a backup directory. Then if I do rm minus r backup, I should see that my backup directory is no longer there. So basically just do whatever you need to do and then show with ls that the backup directory is there. I should say I did record it. So you can, if you're interested at all, you can look at the recording. Okay. So, so that's step one. Step two, create a copy of each of your FASTQ files. So you can do this if you want. We actually did show you how to use a wildcard. So go ahead.
Sorry, when I tried to remove the backup, it said to send into right protected directory backup.
Right, and so that's because we did the chmod, you did the chmod
Right.
minus w. So you can say yes and say why in response, and then it will do the deletion. Or you can be super dangerous and you can do the rm minus fr, the backup directory. So
Yeah, like I said yes, and then it gave me another like remove
Yes.
regular file, and then I said yes to that one, and it said permission denied.
Ooh, interesting. That's exciting. What type PWD? What directory are you in?
Home joking.
Okay. You know, I think what's going on is your backup directory itself is write protected.
Mm-hmm.
So there's a trick where if the directory is write protected and the files are write protected, you can't delete the files without making the directory writable.
Okay.
It's just a fancy way of saying like, I can remove the file, but I can't remove the entry from the directory, so I'm not going to do anything.
So I just need
So-
to have right permissions back.
So what I would do is go, I think you're in the wrong place. So what you
I
should
thought you
do,
said to do it in the home.
did it say in the home? Anyway, I think it doesn't say. So actually if you go to your, so I would go to your DC sample data untrimmed FASTQ and do it there. So let me go ahead and annotate this. Make sure people are starting from their DC sample data untrimmed FASTQ. Okay. So if we're in DC sample data untrimmed, we could do what they're telling us to do, which is copy SRR97 to SRR97, and I'm going to name them .copy, and copy SRR098.fastq to SRR098.fastq.copy, and then make a subdirectory. Okay, so the next step is make a new backup directory, and then use a wildcard to move your backup files to that directory. So that would be make directory new backup, say, and then move star.fastq.copy to new backup. So this is a different remixing of some of the commands we've done, but hopefully it's sort of the trend is clear, right? We're making copies of the files, we're making a new backup directory, and then using a wildcard with the ending with the .fastq.copy to put things in new backup. So now the last step of the request was to change the new backup directory, the permissions on those files, so that they weren't writable. And to do that, you would do chmod -w, new backup /star. And now this ends with the right thing. So we did things in a slightly different way. We made sure we were in the untrimmed fastq directory. We made copies of these .fastq files as .fastq.copy. We made a new directory, new backup, and then we moved the files, the files that we made into that new backup directory. We looked at the directory and we noticed with ls-l, and we noticed that the files were writable. So we went ahead and did this chmod to remove writability from those files. And now we do the ls-l. It's all there. Okay. Any questions at this point? No? Life is good? Okay. Okay, so, and you can see in the solution is probably slightly different. They remove the backup, they copy them to slightly different names, make directory backup, move everything to the backup, and then chmod -w. And at the end, they did the ls -w. Okay, so a couple key points from this. You can view the file contents of files using less, cat, head, or tail. These commands, copy, move, and make directory, are useful for manipulating existing files, creating new directories, yada, yada, yada. You can view file permissions using ls-l. Let me just fix that. Yeah, okay. And the history command and the up arrow on your keyboard can be used to repeat recently used commands. Okay. So at this point, we can do one of three things. I don't think we can get through all of this in under 45 minutes, which would put us over. We could do writing scripts, which we could do in about 15 minutes, to show you what's involved in automating things. And this is, I think, maybe more useful and something we can do in a shorter amount of time, or we could quit. I'm seeing a lot of nodding for the writing scripts. So let me just say this, I'm perfectly happy if you need to go, to just go. So don't feel the need to stay to humor me. But I can go through the scripts in the next 15, 20 minutes, and then we'll call it a day. Okay. All right. So scripts is really where is one of the 2 or 3 places where the power, the power of the fully operational Unix shell comes to mind. Star Wars, never mind. Okay. So and really what it comes down to is how can we automate a commonly used set of commands? And what we mean by automate is essentially replay, script a set of commands that you want to do. And we're going to do, because we haven't really taught you many commands in this workshop, we're going to do like automate the copy commands, I think is what we're going to do. But this can be used for anything that you can run the command line. So if you go back to the lab notes and you look at like what we did with the SAM, all the SAM tools like sort, blah, 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 you can put all of those commands in a single file and run one command and it will execute all of those. And the cool thing is there's 2 cool things, well, there's at least 2 cool things about that. One is it means that once you get that basic set of commands written, you never need to remember it all again. So I actually don't, for SAM tool stuff, I tend not to write scripts. I tend to actually just go back to my own lecture notes and lab notes and rerun that. But the other place where it's really useful is you can figure out how to do it once, and then when you have a new project, copy that file over, modify it to run under new file names, and probably it's going to run correctly, as opposed to going to a new project and you're going to have to figure out the right order of commands for doing alignment and mapping and variant calling and that kind of thing. So really what we're going to talk about today, right now, is how to build one of these scripts. So what we're going to do, what we have to do is use a text editor. So far, I've given you all the files. We created history.txt with that greater than thing, never mind. But mostly we've been working with files that already exist. So how do you create a new file? So what we're going to do is we're going to use a text editor called Nano. What Nano is it's a way of creating text files. So the way you do this is, let's say that sorry, I really can't type today. So we're in this DC sample data untrimmed FASTQ directory. And let's type nano readme.txt. And this brings us into a kind of thing that we haven't really seen before. It's kind of like Less, but it's an interactive program. It's an editor called Nano. And it's just something that's easy to teach and easy to. So the way Nano is laid out is it has a little bit of information at the top, takes over your screen, has a little bit of stuff at the top. It has some instructions at the bottom, some commands at the bottom, and then it has the text editor space. And in here is where we can just type stuff. So in here you can type something like, this is my favorite set of SRR FASTQ files. So you can put, this is my sequencing data from the Pigeon project, blah, blah, blah. And now what you want to be able to do is save this. So we're creating a file called readme.txt. We're putting this text into the file. And so let's save it. There's a couple ways to do it. Let's do it the following way. We're going to use Control-O. This little caret means control, and then O to write the file. So if we hold down Control on your keyboard and say O, going to say what file name do you want to write. And you hit enter for readme.txt. And then we're going to exit. So now you could type some more stuff, or you could exit. And if you type Control X and you've just saved, it will let you exit. And now you're back at the prompt. And when you do an ls, you should now see a new file, readme.txt. That's the file you just created. How would we look at the contents of readme.txt? And so that's literally what we typed in the Nano editor. Depending on how you're logging in, there are other ways of editing these files. So just to confuse you more, if we went and found this directory here, within the Jupyter console, we actually could bring up an editor like this, which displays the same information. So this is all just pointing at, there's many different ways of working with the files, but the contents of the files are the same no matter how you look at them. Okay, so that's how we create. Here. So we can create whatever. There's a lot of discussions. I want to move it back. A lot of discussions about what text editor to use. People on Windows machines should look at something like Notepad++, or RStudio actually can do all of this stuff. Those edit on your local computer, not on remote computers. So you need to figure out how to transfer the file back and forth. The reason we teach Nano is because it's operating on this remote computer, and anywhere where you have shell access, you can use Nano. So there's Notepad++, there's Notepad, there's Emacs, there's Vim, there's gedit, whatever. Whenever somebody tells you to use a different editor, I think the best response is to say, I'm fine with what I'm using right now, but I'll keep it in, I'll come talk to you if I need something better, and then ignore them. How can I move this? There we are. Okay. So, blah, blah, blah. Okay. So I guess I have to show this picture again, geeks and repetitive tasks. What we're talking about now is going the transition from doing everything manually, where we're getting ignored, and now we're writing a script to automate it. We haven't given you a reason why you would get ignored, why you would get annoyed. I just point out that if you end up having to copy if you make it backups of a lot of files, if you had to copy each one, it would get annoying. So you might want to have a script that makes it backup. Sort of a contrived example. A better example is I have 50 FASTQ files. I want to do the same thing to each of the 50 FASTQ files. We're not going to get to that today. So there's a command that was introduced in redirection called the grep. And what grep does is it searches for strings. So what this command does, and you have to go back to the previous lesson that we skipped over to sort of fully go through this, but what this will do is it will pull out all of the sequences that all of the FASTQ sequences that contain and we'll put them in a file called scripted bad reads. So if we ran this, I'm just going to run this, and I'm going to get rid of the $, and we did less scripted bad reads, you would see, we've got all of the bad reads, all the reads that have a pile of ends in them. So suppose that we wanted to do this.
Wait, what are the one and the two?
Yeah, so these are options to grep that pull out the context around the n. It's the details are in the previous lesson that we didn't go through. So all of this is saying is run this command with these options, search for this in the FASTQ files, and save the results in this file. But if we're talking about scripting, this is a long command to remember, and it's something you're probably going to get wrong if you try to retype it from memory. So what you can do instead is put it in a script. So here we're going to run nano again, and we're going to create a new file, a shell script called badreads-script.sh. And I should say you don't have to name shell scripts with a .sh at the end. It's just a convention so that when you do an ls and you see a .sh file, you go, oh, that's a shell script. So to do this, let's do nano, what's it called? Bad reads scripts.sh. Doesn't really matter exactly what it's called, but I'm going to call it what the tutorial does. Run nano. And now we're back in this editor situation. And now I'm going to paste in the thing that I took from the tutorial. And I can sit here and wait for you to retype it. And what this is doing is it's putting this text into this file, badreadscript.sh. And the fact that this text happens to be a shell command doesn't matter yet. It will in a moment, but Nano doesn't care what text you're putting in or what the file name is that you're putting in, and you're just creating a file with this text. So I'll just give you a second. Okay, so again, it doesn't particularly matter that you get the command right. If you get the command wrong, it just won't work, but you'll see the effect of the script anyway. Okay, so now let's write this with Control-O. Control-O, enter, and then Control-X to exit. And now you should see, voila, we have this badreads-scripts.sh. If we type cat badreads-scripts.sh, and I'm using tab completion so I don't have to type the whole thing, you'll see it should look like what you wrote in there. And now we need the magic. We can now run this by typing bash space badreadscripts.sh. So I'm going to type bash badreadscript.sh. And what bash says, what the bash command does, is it says take each line in this file and execute it at the shell. When I run this, it recreates scripted bad reads this very instant with the results that I had. So this is now a saved command that I can rerun every time I add new FASTQ files. I could rerun it, or I could put other commands in it. Now somebody asked earlier, is there a way to annotate that file with what those things mean? And you can put comments in. You go back into nano bad read script. I say, I put a # at the beginning of a line. I say, get a listing of all of the sequences with 8 or however many ends, that is 8 ends in them, and save them to scripted badreads.txt. So, and you can treat this kind of like comments in your lab notebook, which is, I tend to view comments like this as for myself. So if I'm doing something tricky, I put a comment in, and if I'm doing something that I think I'll understand when I look back at it, I don't put a comment in. Or if you work with a large group of, say, undergraduates, you could put in a lot more comments in here to explain to them what you're doing. So if you save this now, and you exit, so Control O and then Enter and then Control X, and now I can run this again, and each time it's going to do the same thing, which is update the scripted bad reads file with whatever I do. So the only way you can tell that things are changing is that the timestamp updates. Okay. I think I'll leave this other stuff alone. It's not really super important. You can actually turn, by using the chmod, you can actually take this shell script and make it into something that you don't have to type bash. It's just now a new program. And the reason I would generally recommend keeping the bash component in there for right now, just to remember. But this is sort of another example of the power of Unix, which is I can put together my own programs very quickly by getting a set of commands together that works, putting them in the shell script file, saving it, and then boom, now I have a new command. So it's programming in effect. The real value of all of this is sort of twofold. One is not having to repeat yourself. I figured out a workflow. I figured out how to do mapping and variant calling, and life is good. And I don't ever want to have to remember those commands again, because memory is my short-term memory is expensive. My long-term memory is expensive. I should only have to remember this stuff once. The other is the reproducibility aspect, which is, well, reproducibility and automation. So reproducibility, you could actually save the script that contains all of your sequence processing commands and contribute that as supplementary material in the paper. And when a reviewer sees that, they go, okay, this person told me exactly what they did, and they would reward that. That is a good concept in theory. In practice, where we find the most value from this is that when 6 months into a project, your advisor says something like, hey, what happens if we redo the mapping, but with different parameters or a different mapper? As long as you've written it all down in this script, you can go in, you can change just the command that does the mapping, and you can rerun everything. You can pretend to your advisor that it was a lot of work, and then you can go to the beach while it runs. Right? So the value is really in the notion that you can go back and you can try different things. You can make copies of this file, and then change those copies and try out new things in those copies. But you'll always be able to rerun what you did before. And the only tricky bit there is that figuring out how to run this, like if something takes 24 hours, there's some extra tricks to like run it. So how many of you have access to like the farm or the Genome Center cluster? You do? So there's a way to, this is how you write the programs that you submit to the job queue. So you can write like 10 of these programs, submit them all to the job queue and walk away, and then come back in a day, and they'll have been done on a variety of computers, and the results will be there. So it's essentially the same thing with a little bit of comments at the top for telling it how much memory and how much time it needs. And we can show you how, if you get to that point where you want to do things like that, we run meet and analyze data here, I think in this room, 3 to 5 p.m. on Thursdays for people that want specific help with their specific projects. We're always happy to just chat about stuff. Feel free to talk to me more about stuff. So I think I'm going to call it quits. We're dangerously close to 12:30. I hope this was sort of leveling and informational. I'll post the video link to the class announcements page underneath thing. And I'm happy to take any questions now or in class or via email. Okay. Let me just show you one more thing just to reassure myself, if nobody else. If you go back to like lab 3 and mapping, whoops, this is the wrong. Okay. So if you go back to like some of the stuff that we did here, well, lab 3 is better. You can actually see, you know, in between some commands that we didn't cover, like curl and tar and make, we're doing cd, copy, make directory, cd, copy. You know, all of these commands that we did today are sort of worked into are what we're running. And I would say, you know, I don't think there's too much value in doing it, but if you were interested in, for the homework, for example, you could make a shell script containing all the BWA commands that are here and have that all just run all the way down through the SAM tools and stuff. You wouldn't need to put in the apt-get stuff, but like the SAM tools commands that do the sorting and indexing and so on, you could put it all in a shell script, and that would be sort of, this is how I did my mapping and my data processing. So, all right, any final questions or comments? Okay, then we'll just call it quits. And next time I'll remember, next week I'll bring cookies or chocolate or something.